Hello everyone and welcome back to lecture 7. So now let's have a look at an example to design a heat exchanger. Okay. So when we are talking about design of a heat exchanger, we said that we are talking about either one of these two problems. So we have either the rating of a heat exchanger, and by rating we mean that the area of heat transfer. So we normally do rating for an existing heat exchanger, so it means that the area of the exchanger is already known to us, and we want to know that if we are changing temperature or conditions, is this area is going to be sufficient to transfer that much of heat load. Okay, so in this case of rating, we need to calculate what is U. Okay, that is the overall heat transfer coefficient, and then we calculate what is delta T. Okay, or corrected delta T, and then we calculate what is the Q available for these new conditions. Okay, while for the case of sizing, we are designing a new heat exchanger, and in this case we know the value of Q, okay, from our heat duty. Okay, so what is the amount of heat that we need to transfer between two streams, so that is known to us. And in this case, again, we calculate the value of U or U actual. Okay, and then we calculate delta T corrected, and then finally we calculate what is the area required for this heat to be transferred. Okay, so these are the two problems. So now let's look at the example for the case of sizing. For the case of rating, it is much more easy because we don't have to calculate the new system. So we are just actually re-evaluating our old existing system. So let's look at the example of sizing. Okay. So for the sizing of a heat exchanger, and again, Q is available to you. So these are some of the simple steps that you can follow to calculate what is the area required for this much heat to be transferred. Okay, so step one is that you have to decide what kind of heat exchanger you are going to use. Are you going to use a double pipe heat exchanger, or are you going to use a multi-tube pass shell and tube heat exchanger, or some other form of heat exchanger? Okay. Step two is that you determine what is the inlet and outlet temperatures of all the streams, or in some cases you need to calculate the value of Q based on this equation. So here this equation, what it shows, that all the heat that is contained in the hot fluid is going to be transferred to the cold fluid, and there is no energy loss. So that is our assumption here. And if, for example, if you know the temperatures of different streams, their mass flow rates and their CPs, you can calculate Q. And in case if Q is given and you don't know one of these temperatures, you can use this equation to calculate the inlet and outlet temperature of these process streams. Okay. Then we have step number 3, and in step number 3, we calculate the or estimate the value of overall heat transfer coefficient by looking at individual heat transfer resistances like film heat transfer coefficients and fouling factors. Okay. And then in step number 4, we calculate what is the actual delta T, so delta T correction, and we can calculate delta T correction by calculating LMTD first and then multiplying this LMTD with the correction factor to get the corrected delta T. The last step is that we use the equation Q is equal to UA delta T, and then we know all the values of U, Q, and delta T, so we can use that equation to calculate the value of A. And our final over selection or sizing process finish when we have selected a type of heat exchanger, let's say a shell and tube heat exchanger that is with an area either equal or above the calculated area. Okay, so let's look at this example and try to see how we can use these steps to find out the details of different parameters. The question is that you have one shell and one shell pass and two tube pass heat exchangers. Okay, so in this question, the question has already given you the type of heat exchanger that you want to use. The question also states that the water flow rate of this quantity is in the tube side at 30 degrees centigrade and is coming out at 80 degrees centigrade. So you have the cold fluid, that is water, and entering at a temperature of 30 degrees centigrade and coming out at a temperature of 80 degrees centigrade. Then you have the hot fluid, that is the hot oil, and it is in the shell. And the hot fluid enters the shell at 130 degrees centigrade and leaves the shell at 80 degrees centigrade. And then you are also given the convection heat transfer for the water and for the oil side or for the shell side. Okay. We also know the value of fouling factors on each side of the tube and the shell. So we have this much is the fouling factor, and we are assuming that we are neglecting any thermal resistance of the tube and the wall. It means that we don't need to consider the conduction resistance. We can only focus on convective resistance for this design. And final question is, what is the overall heat transfer coefficient and the area associated with it? Okay, so let's look at this question. So step one, as I said, we have already our exchanger. We have a shell and tube heat exchanger with one shell pass and two tube passes. Step two is to calculate what is the rate of heat transfer or any other missing parameter. So for that, we look at this equation here. So that is our overall heat transfer equation. Okay. And we know that Q dot is equal to U naught, because we are defining U based on our outer surface area of the tube. A is the surface area, Ft is the correction factor, and delta T is the our log mean temperature difference. So that is the final equation that we need to calculate what is the area associated for this heat to be transferred. So we need to know values of each of these parameters in this equation. The first thing that we need to know is what is the heat required, because we are not given the heat in this case. We are given the flow rate of the cold fluid and the temperatures of the cold fluid. So we need to calculate what is Q based on the energy balance. Okay. So if you use the energy balance equation, we know that the Q of the system from the liquid for the cold liquid is equal to m dot Cp delta T. So this is the T2 minus T1, that is the exit temperature of the fluid, and that is the entering temperature of the fluid. And we can use the values given to us. So we know the flow rate, mass flow rate of the cold fluid. We know its specific heat because it's water. We can get it from the steam table, and we know the entering and exit temperature of the cold fluid. So by using this equation, we can calculate what is the heat requirement of the system. Okay, so you might be in a situation where actually you are given the temperatures of the cold fluid and you are missing the flow rate of the cold fluid, and then you can use and you are also given the temperatures and mass flow rates of the hot fluid, and in that case you can use the for example the delta T balance of heat exchange, hot Cp hot delta T. Okay, so you know this value, 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 but you don't know this value. Okay, in this case you have to equate these two heat transfer systems to calculate the value of m, and as such you can calculate the value of Q. Okay, so there are different questions, for example, with different information provided. Now step 3 is to calculate the overall heat transfer coefficient. Okay, so to do that we go back to our previous parts that we looked at the value of overall heat transfer coefficient, that it accounts for all the thermal resistances involved in the system. And here we are assuming that the thermal resistance due to conduction is negligible, so that's why we simplify this equation in this form, where we have the contribution from convective resistances and due to the fouling factors. Okay, so if we because we know the value of all these parameters, so we know what is the value of H and F for inlet inside and outside of the tube. So if you just plug the value, you know what is the overall actual heat transfer coefficient. Okay, then step 4, we need to calculate what is the driving force for the system, because we have Q is equal to UA delta T corrected. Okay, so to calculate delta T corrected, we need to first calculate what is LMTD. So to do that, we use this information. Okay, so we know the temperatures of the inlet and outlet of the cold fluid. We know the temperatures of inlet and outlet of the hot fluid, and we can calculate delta T1 and delta T2, and then we use this equation to calculate what is LMTD. Okay, and in this case we have this is a special case, because if you look at that, the delta T is constant along the length of the exchanger. Okay, so it means you don't really need to calculate delta T, LM delta T, because it is going to be same as 50 degrees centigrade, because the temperature driving force is not changing along the length of the heat exchanger. Okay, and as such the value of LMTD and arithmetic mean temperature difference would be also the same. Okay, so this is a special case, but in for example in exam you might not have this case, and then you have to use this equation here to calculate what is LMTD of the system. We know the value of LMTD. Now we need to correct our delta T driving force by multiplying LMTD with FT. So we need to calculate what is FT. Okay, and to do that we need to calculate the value of P and R. Okay, and as I said here, you don't need to memorize these values, because these values are given in the figure. So for example, for one shell and two tube pass system, you have this diagram provided to you, and if you look at that, at the bottom of this diagram you are given the definition of P and R. Okay, so when you are given these values, please be careful that you use the right temperature. So lowercase t is for the tube side, while the capital T is for the shell side. Okay, so what we have to do, we have to calculate the value of P, that is from the previous example we have 0.5 and 1. So we know the value of P is 0.5, so we locate it on the x-axis. So that is our value of R, and that is our value of P. So we go from our value of P to the line where it touches the value for R, that is 1. Okay, and then from this point we go towards our y-axis to calculate the value of Ft. Okay, and in this case our value of Ft is 0.81. We use this information and calculate our delta T correction by multiplying Ft with LMTD. So our final corrected temperature difference along the length of heat exchanger is 40.5 Kelvin. Okay. And now the last step, we know the value of U, we know the value of delta T correction, we know the value of Q that is given in the question. So if you rearrange this equation in the form of area, so if you now put the value of these parameters, so we can calculate the final area of the heat exchanger is 107 meters square, that is required to perform this amount of heat exchange. So that is all for this part. Thank you for your time.